Hello and welcome to this research seminar series, Radon in North Dakota. I'm Mark Williamson, a research assistant professor in population health and statistician for the Biostatistics, Epidemiology, and Research Design Center at UND. So let's get started here. What is radon? Why should we care about it? Well, radon is a naturally occurring radioactive gas. It's colorless, odorless, and tasteless. So therefore, you really can't detect it unless you have some sort of device to detect radon. Otherwise, you have no idea it's there. Now, because it's radioactive, and it actually undergoes radioactive decay, so its elements break down from a heavier element to a lighter element through radioactive decay, and this emits ionizing radiation. Now, ionizing radiation comes in several different forms. There's the electromagnetic radiation that you might be maybe more familiar with. So things like visible light, infrared, or even radio waves, those are all types of electromagnetic radiation that really aren't dangerous. They're non-ionizing. They have less energy, while ionizing radiation have more energy. They're things like UV, X-ray, gamma rays, things that really can start to do damage with all the energy they have. So that's just one kind of ionizing radiation. There's another type is actually, so that's the electromagnetic. There's also what's called particle flow, where particles are actually released from, say, the radioactive product. There's alpha and beta radiation, and we'll see more in detail, especially alpha radiation. That's really what happens when we're talking about radiation and radon. Now, radon, it's radioactive. You might think it may be weird or unnatural. It's actually perfectly natural. It comes from the natural breakdown of uranium and thorium in the ground. There's actually multiple isotopes. That means multiple different numbers of neutrons in it, because what makes an atom is the atomic number. So radon's, it's 86, but it can have different numbers of neutrons, giving a total mass number, which is protons plus neutrons in difference. Now, there's the most common isotope is going to be radon-222. That's the most common. Again, you can see this chain of radioactive material. So usually starts with uranium, that decays the thorium, etc., all the way down to radon. And actually, the most proximate radioactive material is actually radium. And that's actually, if you want to produce radon gas, you actually get radium. Anyways, and then that'll further decay into other radioactive parts until it finally gets to a non-reactive lead. Now, again, there are 37 actually different possible isotopes of radium. Really, there's only, other than 222, which is the most stable, there's only 5 other ones that really occur in trace quantities within nature, not produced in a lab. So that's 217, 218, 223, 224, and 226. So that is a primer of radon. So let's turn a little bit more to its chemistry, its chemical properties. So again, I told you its atomic number is 86. So radon is over here. It has 86 protons and then a variable number of neutrons depending on what isotope it is. It is actually a noble gas here, so it doesn't really react with other elements, just like things like helium, neon. Those are noble gases. They aren't reactive. It reacts in the way of essentially chemical reaction. Now, obviously, it's radioactive, and there are actually no stable isotopes. So if you have radon, it's going to decay into something else. It just depends how fast, depending on the isotope. And again, the atomic mass ranges from 195 to 231. And so if we change out here and look at the radioactive elements, we can see here radon is sort of at the lower end of radioactive elements. The elements higher than radon, they're all radioactive. And then there's a couple of these polonium and acetylene are also radioactive. Actually, though, an interesting outlier, technetium is the lightest element whose isotopes are all radioactive. But then all these ones in the darker, I guess, grayish green, those will have stable isotopes that aren't radioactive. Now, some of these isotopes, like, say, bismuth, radon can actually decay into bismuth, and it can actually decay into a radioactive isotope of bismuth, but not all bismuth is radioactive. So big thing with the chemistry of radon, everything, it's all radioactive. There are no non-radioactive radon isotopes available in nature. So let's go and talk a little bit more about the physics of radon. So going into a bit of radioactive decay. So I told you there's different kinds of radioactive decay. The most common, the most typical thing that we're going to talk about with radon is alpha decay. This is where radon 222, so the top shows the atomic mass, so that's neutrons and protons, and then the bottom is, the top is the atomic mass, protons and neutrons, or mass number, and then the bottom is the atomic number, the number of protons. We can see here that it'll decay into polonium and a helium atom. We can see here that it goes down from 222 to 218, and then this is that 4 that was lost. Similarly, 86 to 84, the 2 that was lost here. And this is what's known as alpha decay. And because essentially what comes out of it, what decays out of it, is an alpha particle, also known as the helium atom. And this type of radiation, alpha decay, is fairly innocuous in most situations because it only happens at a short distance, and actually you really can stop this radiation with a sheet of paper. That's all it takes. So when you think of like radioactivity, you probably think of like, well, we need to be in a lead bunker to keep it from getting to us. That's, higher forms of radiation like gamma radiation. Yeah, sure, maybe that's true, but for alpha radiation, it's actually fairly benign in most circumstances, though we'll see later why it is actually a problem with radon and human health. Now, again, when radioactive radon decays, it forms daughter elements, so decay products. So the daughter elements here is polonium and helium. Now, there is a very uncommon type of radiation that it theoretically can do, though it's not by no means is it very common when we think of radon decay. So this is a beta minus decay, where actually radon emits a negative beta particle and then a francium atom. And so that's one way to do it, and it kind of shows here, and it also releases energy. I think it releases against a negative beta particle. The negative beta particle is an electron. It also produces an anti-neutrino to keep all the charge and mass and all that sort of physical constants straight. Anyways, but to sum all this up, there's a lot of physics going on, a lot of radioactivity. Most of the time, when we think of radon, we're talking about alpha particle generation. So, where is radon? Why should we care about it? Well, radon is, again, naturally forms from the environment in the soil from radioactive components, and then it can come up into, namely, obviously it'll emit out into the atmosphere, but since there's so much of it, it really disperses quickly. Where radon really starts to pull up is in houses and other buildings. So it can come up through the bedrock, especially fractures. It can come out through the soil, in well water too. Yeah, so radon can be quite prevalent in water, though typically it's more in the gaseous form in low-lying areas, especially in basements. It can go up through fittings, cracks, ground, especially like sub pumps, drains, areas like that, windows, cracks, etc. And actually sometimes radon can get into houses easier, newer houses easier, because if there's like, say, a sub pump or something, but then otherwise it's really sealed well, it gets in and it's hard to get out. And especially in changes in temperature, especially cold winters, often radon can pull up more here. So, and again, anywhere that there's a lot of natural radiation in the ground, houses that it can get into through cracks or other areas, it's going to get in and stay there. And now I did tell you that it decays. So radon decays, but if it, so you might think that it would go away after a while, but the fact that it's constantly being replenished by seeping back in and then decaying into stable elements, there'll always sort of be a baseline level of radon. So if the chemical and sort of geological formations in the area where, say, a house is are stable, the radon generation will be stable unless there's interventions into the house or structure. And across the U.S., radon has differing levels of prevalence. Now, an important key to note here is concentration. So there is this sort of cutoff value is 4 picocuries per liter. That's a certain amount of concentration where it starts to become a health problem. So that's sort of the cutoff. So if there's a structure, a house, building, whatever, has 4 picocuries per liter or more, that should be dealt with. And so in this map of U.S. counties here, we see red is the danger zone. Zone 2 is sort of intermediate. It's 2 to 4, so it's not great, but not terrible. And then yellow is sort of fine. You can see here, especially like the part of the South or even the West Coast are pretty good. There's orange otherwise, but especially the Midwest is very high. In fact, North Dakota, you notice here on this map, all the counties are red. In fact, North Dakota has some of the highest radon levels. Depending on what county metrics you use, most, if not all, North Dakota counties average a radon level above the cutoff value that should be remediated. Here's just another set of data, and you can see here that this is on a finer scale, and you can see how that affects places like Grand Forks County is particularly high. So what are the effects of radon? Why should we even care? Well, it's radioactive, which probably means it's not the best for human health. And if you thought that, you would be correct. Again, we're going back to this 4 picocuries per liter. That is the cutoff from the EPA, the Environmental Protection Agency. There's really no safe level of radioactive exposure, but 4 is sort of a cut point where higher than that, you start to really get increases in the risk of lung cancer. Why lung cancer? Well, that's because I talked about it being alpha radiation, so it's short distance, it can be stopped by a piece of paper. But the problem is radon is a gas. You breathe it into your lungs, which then it's right next to your lungs, and your lungs are very thin, and so it can decay, and its decay products can decay and do damage to the lungs and actually cause mutations in the lungs. That's where you get lung cancer, damaging cells, damaging DNA, leading to misrepair, and eventually can increase the risk of cancerous mutations. So, radon is actually the second leading cause of lung cancer death. The first, to no surprise, is smoking, but after smoking, it's lung cancer, and actually 4 picocuries per liter is equivalent to 200 chest x-rays per year. So that's as much radiation as, 200 chest x-rays. So that's a lot of radiation. Here's a little picture here. You can see here what happens is radon progeny, so the decay products, can attach to things like dust particles. You breathe those in, it's right in your lungs, and the radon progeny can actually attach to the lung walls and decay, causing damage to cells. Here's just some comparisons of radon effects of death per year. So it's causes more death per year than drunk driving, falls in the home, drowning, and even home fires. So it is a pretty significant human health hazard. But it actually gets worse than that. So now, if you've never smoked, the risks aren't great. Again, at that 4 picocurie, it's about the risk of dying in a car crash. If you get up to something really high, like 20 picocuries, it's like 35 times the risk of drowning. But it's actually worse if you're smoking, not just smoking and radon both cause it. It's almost like a synergistic that actually you can go up to 5 or even almost 10 times the risk of a non-smoker. So 4 picocuries, 5 times the risk of dying in a car crash. 20, 250 times the risk of drowning. So it can have even higher health risks depending on behaviors. So the really big issue with radon is I've kind of walked through its characteristics, showing that it's a major carcinogen and it can be highly prevalent in houses and other buildings. But the big issue is is not that it's preventable. It's actually quite preventable. If you know that you have high radon, you can remediate it through various processes. The big problem is it's difficult to get people to care about it because it's invisible, odorless, tasteless, and has a long latency. So it might kill you in 20, 30 years, but you can't detect it now, and it might be a hassle to deal with it in the short term. So radon is not just a health issue, it's also a communication issue. It's hard to get people to care about it. Just like, say, high blood pressure can lead to all sorts of health issues, and it's fairly preventable if people know about it, which is hard to detect without doing specific tests and treating it. So what can you actually do about radon? Well, the first and foremost, you can test for radon. In my neck of the woods, at least at a certain point, the Grand Forks Public Health Department offered free short-term radon tests. These come in the form like here. They have this, I think, activated charcoal, and you set it out, and after 48 hours, you send it back to a lab, and they give you your tests. Stores like Walmart and Menards, of course, also carry them. They're fairly affordable. But if you really want to get quick, accurate feedback and not have to worry about sending things back and all that latency, you can actually, the Grand Forks Public Library just finalized a continuous radon monitor lending library. So you can actually go, if you live in the Grand Forks area, go and check out a radon test kit and use a continuous radon monitor to test radon in your house. So that's what you can do to start with radon, is test for it. Next, if you have high radon, 4 picocuries or higher, you can remediate your house. Now, sometimes it might be as simply as covering your sump pump. There's, in fact, even things for like $100 that might do it, of like a sump pump cover or other ways to seal up. Sometimes basements with bathrooms, how they're set up with like a tub or something, you can sometimes just put stuff underneath the foundation. Or if that doesn't work, that isn't the case, certainly some sort of active remediation is another step. This can range to a couple $1,000s. Not great, but certainly within target if you really work for it. And then essentially what happens with these here is you have some sort of suction pipe, whether interiorly or externally, and then have a fan more like at the attic to actively pump air, to suck air up and out so that the radon doesn't stay and pool up. And again, in the North Dakota area, there are several people who can either measure radon and mitigate radon or do both. And of course, there's certainly resources for doing it yourself, or finding the materials that a contractor could help you with. Another thing you can certainly do is research on radon. Radon is becoming more important every day, not just for lung health cancer. There's implications, for example, in other cancers like chronic lymphocytic leukemia. There's some evidence that higher rates of mean radon level across counties in the Midwest, including North Dakota, were linked with higher age-adjusted leukemia rates. There's also, here's just a smattering of studies, including modeling how radon comes out of the soil. And in fact, there are people who have built experimental radon test chambers for animal research. Again, if you want to do some research yourself, North Dakota has a data set. It's a little hard to find. You have to go to this website here, but there's a radon home survey that was done in 1988 to get survey statistics by parameter, county, and city and county. So you can, and there are things like this available for other states as well. So you can figure out what's out there, what levels of radon are present. And another big research that I'm working hard on is actually creating a radon test chamber for UND. Great advancement for environmental animal researchers. I mean, it's easily a source of half a dozen research papers a year. And given that North Dakota has such a high level of radon, there's no reason that UND, especially the School of Medicine, couldn't be the epicenter of radon research and really connect with a lot of other departments on learning more about radon, especially with different health. Because again, not just things like cancer, I talked about other kinds of leukemia. There's growing evidence that might have to do with things like stroke perhaps even like respiratory diseases, etc. So there's a lot to do with radon. And again, the big problem with radon is it's hard to get people to care about it and test for it and remediate it. And so a big piece of research is actually radon communication. How can you communicate radon risk to the public so that they can act on it? So actually, I know people in my department of and also the Department of Communication, Grand Forks, have done clinical trials to try to improve radon knowledge and test kit use through things like apps. And you can even do it on a very low level, very basic level. There, in various parts of the country, there's poster contests about radon awareness that you can do with kids. And finally, of course, what to do with research, whatever you'd be most interested in, your research project here. There's no reason why you can't find a way to improve radon health risks and understanding through a special research project. To close, I'd like to acknowledge my supervisor and collaborator, Dr. Gary Swartz, the chair of the Population Health Department. A lot of this radon research has been his impetus, and so he's doing a great job. Also, to reach out and thank is Dr. Soo-Jung Kim, Dr. Marion Klug, who also have done research with him and myself on radon research. Also, the ROAR, the Radon Outreach and Research Network, that's Dr. Gary Schwartz's sort of brainchild there of trying to get this radon information and research out to the public. And finally, DaCCoTA, the DaCCoTA Community Collaborative on Translational Activity, where a lot of my funding comes from. Thanks for joining me for this research seminar. Have a great day.